All right, so hello everyone. Welcome to the seventh lecture on open systems. And last week, how did we start last week? We talked about, we tried to talk about computability of stochastic maps, right? And so we discovered that there are some problems with computability, right? Because, stochastic map is not only is it time-ordered exponent, so there is one difficulty with that, but also there is an average over stochastic process, right? We knew that from previous experiences that time ordering can be defeated with dynamical equations, right? But what about the average? And we quickly checked and discovered that, well, we don't have, because of average, we don't have dynamical equation for free, at least, right? And like to isolate the problem, the new problem, we temporarily switch to the pure dephasing case where the time ordering is not needed because the generator is constant in pure dephasing, so that we could isolate only the issue with averaging. And then we will in pure dephasing case, we were dealing with what we came to call coherence functions, which are just some things of this form, right? SDS, so just exponent, normal number exponent, right? And right, and this bad boy, this kind of guy, does not satisfy. There is no dynamical equation for this guy. It's not something like blah, blah, blah and W, right? It doesn't work like that for free, at least, right? And this is and you get this because of the averaging, right? Because you average exponent, the F falls down, but it's still caught by the average, and you don't reconstitute the exponent on the right-hand side of the equation. So we came up with a technology to deal with this issue. The technology is called cumulant expansion, right? So we postulated essentially that the average exp, we said, what if it was just an x of something? Something that can be written down as a series. And right, there is time dependence there. And the elements in the series, the terms in the series, we call them cumulants. We chose for them this notation that is very similar to the notation for expectation values, for averages, for moments, right? And so n goes from 1 to infinity. And this guy here, right, we chose a symbol for it, high f of t is a cumulant series, right? And we figure out quite quickly that this implicit definition is well formulated, that the cumulants can be like iteratively, successive orders of cumulants can be found, the equations can be solved and stuff like that. We discussed some properties of cumulants. I was advocating for them that they are the best things since sliced bread and stuff like that, and I still believe that. But in the end, our mission was to do something about this. And well, if you say that your W is W of t is actually exponent of some function of t, well, that's essentially by definition when you take a derivative high f, right, of t, you get high dot times e f of t, right? You have to get a dynamical equation, at least formally. because this thing here, the derivative of cumulant series, is still like a formal series. If you want to solve the equation, you have to substitute for it some finite form inscription, right? Some function of time. So here comes the approximations. The simplest one would be to simply take this whole series and cut it on some finite order. So you would say that we could say that nth order approx, that would be just taking the taking high of t and approximating by a sum that goes from 1 to some finite n0, right? Lambda n factorial, all the integrals, right? Blah, blah, blah. It's one and cumulants. Since cumulants can be successively determined, this thing in principle could be computed. Derivative could be calculated. You could substitute it in here and you could just solve the equation. Or, well, if you can compute this sum, you could just plug it into the exponent and you get your coherence function. But the point that you get dynamical equation that can be solved also stands, right? So that was our project last week, and I ended on this mysterious what do you say it, remark that well, there are some things about cutting the series on finite order. So as it turns out, there is a mathematical theorem that tells us that if this cumulant series is to represent a real stochastic process f, it either has to have at most two non-zero cumulants, so the first one and the second one, or infinitely many cumulants are non-zero. In other words, the theorem, the Marcinkiewicz theorem, as it's called, it tells us that either you have the full series, the infinite series, or you cut it on the second order. Otherwise, the stochastic process represented by the series wouldn't be a real stochastic process, which in our case, you would translate it to, well, if it's something gets broken, then maybe the W approximated by your series that you cut on some order n0 would start to behave weirdly. Like, for example, it would become greater than 1, which is, from definitions, impossible, right? It's between the modulus of W is no greater than 1, because it's an exponent, average exponent, right? But if something goes wrong, it can actually start to diverge, for example. And my argument was that don't worry about this too much. This is a theorem, mathematical theorem. So it's a binary state, right? It's either you satisfy it or not. But in practice, as long as your high is well approximated by this finite sum, so there is some error, some epsilon, right? Error. Then you might not satisfy the theorem strictly speaking, but the aberrant behaviors on W that would come up because you violate the theorem would be also of the same order of your error, right? So as long as your approximation is a good approximation, everything is fine. Okay, even though formally, you can argue your theorems are not satisfied. But it also leads us to this observation that there is something special about cutting. So you have all those stochastic processes, infinitely many different stochastic processes, and it's seemingly you can categorize them by those that have two cumulants and those that have infinitely many cumulants. So there is something special about those two cumulants. Or the first one is an average, so it's kind of it's never important. So it's like essentially there is only one processes with this one essential cumulant, something special about them, and indeed they are special, and they have their own name. They are called Gaussian processes. So I want to talk a little bit about Gaussian processes, but before I want to make another the abstract remark, because we're talking about stochastic process, right? We started with well, stochastic maps, but also stochastic processes, right? We started by stochastic process is defined by this functional probability distribution, right? If you remember, there was a distribution on the space of trajectories, right? Trajectories which are functions, right? And this defines the process. Then we said that okay, this is like a formal object, master object, but in practice you can like switch between it and this family of joint probability distributions, which are normal distributions, standard multi-time probability distributions, and they are like equivalent to this master distribution, but the price you're paying for description in terms of those guys, you have to have infinite number of them for every partitioning, for every time grid, essentially, right? And they are equivalent description in the sense that if you have this guy, by taking a discrete time restriction, you get those guys. And there is also, if you have those guys, you can go here. This is like a extension theorem. The procedure maybe is not very useful in practice, but there is if you have them in principle, you could reconstruct this guy, which is like the master description, let's call it. But now more objects came up, okay? Because as it turns out, this W, this coherence function, it's actually a special case of something that's called a characteristic function of process. Because if you can think, if you notice, so if you take exponent I lambda 0 F S ds and you take average, well, that's, this is a I lambda 0 F S ds PF F df, right? Average is a integral with the distribution. So this thing is like a kind of Fourier transform of probability distribution. In fact, maybe it doesn't look like a Fourier transform for you, but if you look at this guy, this is essentially a kind of this integral lambda fs ds. So this is actually a inner product between two functions, right? You can think of it as an inner product between f, so trajectory, and the constant function, right? So something like lambda, all right? So this is, I said this is a special case because this is Fourier transform, but with this frequency taken as a flat function, okay, on some interval. So if you can imagine, this is having this characteristic function, this Fourier transform, is also an alternative equivalent way to describe stochastic process, because there is, again, it's maybe not very easy, but if this is a Fourier transform, Fourier transforms can be inverted, right? And I don't know the exact mathematical details about this, but there are some theorems that allow you to formalize this inversion. So in a sense, if you have a characteristic function, you have W, in a sense, this is also like another way to describe stochastic process, another way to characterize it. I lost my, so we can write something like this. But then, if you have this W, this characteristic function, there's another layer on top of that. Because if you take this guy and you take a series expansion of exponent, you will get a series of moments, right? You will get moments. Whole family, infinite family of moments. Which so you have characteristic function, you can extract from it moments, all the moments, and the other way around. If you have all moments, you can reconstruct characteristic function from which you can get the probability distribution. So moments is another way to characterize the stochastic process. So you have a probability distribution for trajectories. You have those family of joint probability distributions. You have characteristic function. You have family of moments, and also you have a family of cumulants. Right? That's what we did last week. So that's why so you have moments or cumulants or characteristic function or multi-time joint probability distributions or functional probability distributions. All these guys are interchangeable. Depending on the context, one representation might be more useful than the other and stuff like that. But it's kind of it's useful to remember that all those things are different ways to characterize, to describe stochastic process. And that's why this Marcinkiewicz theorem actually works, because the Marcinkiewicz theorem is some theorem from algebra. It talks about some serious stuff, some non-negativity, positive semi-definiteness, stuff like it's very abstract. But once you apply it to cumulant series, the result is what I said. Either it has two non-zero cumulants or infinitely many non-zero cumulants. And because cumulant series or cumulants are one of the ways to characterize process, that's why you can conclude from that that there is cumulant series that describes a real process, real stochastic process, has to have those properties, right? Because cumulant series is a way to describe stochastic process. So maybe a little bit abstract stuff, but I felt I had to make it more clear that we switch between those different pictures, different representations, but they play the same role, okay? All right, so Gaussian processes. Let's put a line here. So Gaussian process is a process for which high G of t it has I lambda G. I need integral, sorry. Integral S ds minus lambda squared. We can write it like this. ds2 0 S2 ds1 S2 S1 second cumulant and nothing more, okay? plus 0. This is the standard way to define a Gaussian process. The process for which you have at most two non-zero cumulants. Typically, you just say that the average is 0, or the first cumulant is 0 because it changes nothing. So your focus is squarely on the second cumulant, which we know from previous lecture that this is a autocorrelation function also. So it's like a very let's say well-known in applications kind of object. Okay, and so Gaussian processes are fairly popular in applications where one reason is because they are extremely simple, right? Because you just basically any shape of this second cumulant will do, and you have your stochastic process. Okay, so that's very useful. But the other reason is more important, that it's actually very often a good model of real physical and sometimes even non-physical systems. Non-physical, I'm thinking about stuff like stock market or something. So people try to model them with stochastic processes, and Gaussian processes are useful there. And the reason why it's often a good model is it's a phenomenon that's explained by a so-called central limit theorem. There is something that's called central limit theorem. And it kind of explains why Gaussian processes are common in nature, let's say, common in systems is all over the place. And the simplest form of central limit theorem is for the following situation. It's like you say, take a process G of T. It is actually a combination of some number n of independent processes. Let me write it like this: I a t and I a independent, or maybe mutual independent. I would write this. So Fi are mutually independent, independent, okay? And this is kind of important thing, that is a combination of independent processes that are like weighted, let's say maybe not weighted by weakened by this factor 1 over square root of n. We'll see why this comes into play. And the central limit theorem tells us that when this n goes to infinity, G becomes Gaussian, even if Fi are not Gaussian. Okay, so you can imagine that you have some system where there is a noise in the system, right? So you model this noise with a stochastic process. Like it could be a evolution of quantum system, but maybe some stock prices or whatever, right? And you like imagine, okay, well, so what is the source of this noise? And you think, well, there's probably a multitude of different sources actually, and the system experienced like the whole superposition of those contributions from all around. And those contributions are probably independent of each other because they come from completely different like physical sources. So you take your noise in the system is a sum of large number of fairly weak and rather independent contributors, right? So this is like seemingly a very good description of many scenarios. And the central limit theorem tells you when you are at this kind of setup, when the number of those contributors is very large, your overall noise starts to become Gaussian, or in other words, the second cumulant starts to dominate over other cumulants, which is, you can neglect all the rest because the second is what drives everything. And I thought we can do the quick calculation to actually show that what happens here, and maybe to emphasize the role this damping factor plays here. So if we have so to get the simplest possible variation of central limit theorem, we will make another assumption that not only Fi's are independent, but they are also they have the same distributions, or in other words, they have the same form of cumulants. They're independent of each other, but each of them behaves the same. Okay, so in other words, so for every I different than J, and every n, we want to say that I Sn is one I cumulant equals Fj Sn Fj S1 cumulant. So this is what I mean, that they are the same distribution. And let's just call it F0. If all the same, we can just, which index we use doesn't matter anymore. So let's use the universals index 0. And we will also assume that F0S, so the average is 0, okay? So they are n independent, equal, the same distributions, and 0 average. This is the simplest possible setup. And once you have this, the rest is quite simple. You just have to check what is the form of cumulants of G, of this combination of Fs. And this is just a straightforward calculation. So you take G Sn GS1 and you take cumulant, which means that we can take out the factor square root of n power n, and we have sums I from 1 to n of Fi's Sn, sum I1 to n Fis1, and take cumulant of everything. And now here comes the nice thing about cumulants. If you remember, cumulants are statistically irreducible, right? So there is no, if Fi is independent of Fj, that means there is no mixed cumulant. So the cumulant of sum is a sum of cumulants, right? So this thing simplifies immediately 1 over n, sum over I from 1 to n, Fi Sn S and I, right? Because all mixed cumulants are 0 because processes are independent. And since all cumulants, each process, each Fi has the same cumulants, right? So the sum here, these cumulants don't depend on index I, essentially. So this again simplifies to 1 over n over 2 minus 1. And we have this universal cumulant. Zero. Okay, that's a thing. And now we can just take the limit, go to the limit with n to infinity. And the only thing that depends on n is this factor here. And as you can see, only for small n equal 2, this for small n equal 2, so for second cumulant, this is identity. And for all other n's, it's just something 1 over some power of n, which goes to 0 in the limit. So in other words, it's f0 s2, f0 s1 cumulant when n equals 2 and 0 otherwise. Okay? Which means that G in this limit has only one non-zero cumulant, the second one, therefore it's Gaussian. This is the idea. And in more complicated, you can show this for more complicated scenarios. You just need a lot in almost roughly independent processes that are weak. Okay, this factor 1 over square root of n is what takes care of weakness. And you know, more fancy techniques are needed then to show that the second cumulant will be those situations will start to dominate over the rest. But this is the cleanest, the simplest one. And you can see that there is taking a square root of n here is kind of, if you take something else, you wouldn't get the result, right? If you just take 1 over n, then everything would be 0. If you take weaker, let's say to the power 1/3, then what would happen if here is 3? If you take something weaker, you would have the lower cumulants would explode then, because you have finite cumulant, but multiplied by the number of contributors. And if you don't, right, because see, this is n times the cumulant, right? So if this is not weaker than square root, then this n in numerator will start to dominate, right? So you will get some explosions. So this is square root is just fine. Okay, this is the just fine spot to get this correct limit. And you can think of it as like, because you want to take a limit where the number of contributors goes to infinity, but you want some constraints in it, right? Because you can think, okay, this noise this is like some external force field. You can think of it as an external force field. So it does some work, right, when it wiggles. So it brings in power. So it brings some energy on average, into the system. So if you just make it a sum of processes, then each component will bring you its own work, right? Its own energy. So you want to like, okay, I want to take infinitely many of them, but in such a way that this power output is like, let's say, fixed. It's held constant. So you have to like figure out how to scale the contribution from each guy when you increase the number of contributors to keep the power in check. And this square root of n is the factor you need to keep the power in check, essentially, to keep the power constant. So that's why it's here. So those are Gaussian processes. Good. There are no other categories like that. Okay, so Gaussian processes are second cumulant, but for others, there's no like universal categories beyond that. Okay, this one is universal, let's say, but the others are not. So for example, random telegraph noise, we know that it's non-Gaussian. We know it's not Gaussian because we checked that coherence function did not satisfy the dynamical equation. Therefore, the cumulant series has to be one of those infinitely long cumulant series. And in fact, you can check that the cumulants are actually, you can calculate all of them and they don't disappear. Maybe like odd ones will disappear, but there will still be infinite number of non-zero cumulants. So, that's it. In a sense, although this is kind of abstract, but I think it could be argued that random telegraph noise is actually the most non-Gaussian process. How do you define most non-Gaussian? This is like a longer discussion, but I think you can make a case, can make an argument that it's like the most non-Gaussian. Maybe if you're interested, you can ask me later. I can give you some rundown of the argument. Anyways, let's with that out of the way, we can carry on because on the face of it, we want to compute stochastic maps, not to talk about stochastic processes and cumulants all day. Although I could, but the objective was to actually couple quantum system to stochastic process and see what's going on. And so we kind of, with this cumulant expansion, with the cutting the cumulant series or any other approximation that allows you to write it down as some finite form function, you recover the dynamical equation that defeats the average, takes care of the average, but this was for pure dephasing case. Okay, so now let's go back to the general case of when the time ordering is also in effect, and this will bring us to the next section 6.4, and the section is called super or super-cumulant. Cumulant expansion. All right. Of course, there's something has to become super eventually. Okay, so we have our general form of stochastic map. So the time ordering is here. It cannot be neglected. Or no, not neglected, but it's necessary to use it. Yes, we have an average. Right, and as it turns out, the cumulants of process F, they can be incorporated into this time-ordered exponent as well, actually. And the thing you get, you can actually rewrite this guy as a time-ordered exponent, and the ordering is over these. I mean, the shape is kind of intuitive. So we have time-ordered integral here. We have a cumulant, Sn, multiplies everything. And these are here, S1. All right? It's kind of intuitive shape. Although showing that this actually is the case is a hell. It's hell. It's hellish. It's really oof. So there is so we have a right. So this is this formula I just wrote down, and there is an assignment 23 to verify it, and it's not a real assignment for you to do, but take a look at it. because it's a look guys, it's kind of terrible. Okay, it's kind of terrible. If you are really interested, you are glutton for punishment. You can take a look what's going on there. But it's kind of oh, it's horrible. Yeah, I mean, it was a really tough calculation. It was really annoying to do, but I did it, and you can actually write it like that. But the thing is that the time ordering is still over these, okay? These which are come in this whole series, right? It's kind of complicated. So, but you know, this is a form. So maybe it's actually enough. Maybe this is enough to get the dynamical equation. Who knows? We have to check. So to simplify our lives a little bit, let us assume, since we learn about Gaussian processes, assume that f t is Gaussian. Is Gaussian. So in other words, f is G. Okay, we don't need two cumulants. This will simplify things a bit for us because this means. Let me hide this. Okay. Simplifies things because now the UT0 it's still time ordering. We have exponent. Oh, and then and Gaussian and zero average to make it even simpler. If we do that, then this all kind of simplifies to there's only one term in the exponent. S1, GS2, GS1, VS2, VS1. Okay, so this looks kind of handsome, although this time ordering here is kind of threatening looking, but maybe everything is fine. Who knows? So let's try derivative. Maybe we'll actually get our dynamical equation. Who knows? So we come in with derivative. So we can get in derivative under the time ordering. Just to show what's going on here. Cumulant. PS2, VS1. Well, exponent, I know how to calculate derivative of that. It's not that complicated. So we get here minus, I see an error here. There is no I, okay, because it's a minus I squared, so it's just minus lambda squared. And yeah, so only one integral will remain. Let's call it S1. We will have G T G S1. This is okay. This is still okay. VT VS1 and exponent T TS2 S2 DS1 cumulant and V's and close the time ordering. So that's okay. That's kind of okay, I guess. So there are some things we can do here. Because we have to evaluate time ordering, right, to proceed. So we can pull out the numbers. They don't affect us. Time ordering doesn't care about those. Well, we have here VT at the very extreme on the left, right? And this T is actually the latest time among all V's present in this whole expression, right? Because all guys that comes from this integration, the T is the limit, upper limit, so all of them are a little bit later than earlier, sorry, than T. So this guy will always be on the left after ordering. So we can just already pull it out from under the time ordering. But VS1, it's from S1 can be anywhere between 0 and T, right? So its order, if you compare to V's that are inside the exponent, it's indeterminate. I mean, it's all over the place, right? In other words, there's no easy way to evaluate T. In other words, VS1 cannot be pulled out. It just has to stay there. And this is bad news because we don't reconstitute the stochastic map, even though we took Gaussian approximation to cumulants of stochastic process, the time ordering still beat us in the rear. Okay, this guy is here. This means that we don't get time ordered exponent, we have time ordered V times exponent. So still no dynamical equation. And the issue here is not the average, it's not the cumulants. The issue is that this time ordering we are using here, it's just too fine-grained, right? If it only was smarter or more coarse-grained, it treated the whole exponent as one atomic expression, that would be excellent. Then after derivative, we would reconstitute everything on the right-hand side, it would be perfect. But this guy is just annoying. It's just too fine-grained. So what can we do about that? Well, we have this power over time ordering. We have this specialized time orderings. So let's just impose some stuff, like with cumulants, right? We said, okay, we needed this average exponent to actually be exponent of something. So we postulated implicit definition. We postulated implicit definition. And so what's going on? So here we want this time ordered exponent to be exponent that's time ordered a little bit more coarsely, not so finely. So let's just postulate this. So consider an implicit definition of super-cumulants. So we take our time ordered V. So we take our stochastic map. Averaged, or any other form you want. And we want to say, okay, so let's suppose that it's also time ordered exponent. Time ordering goes, sorry, wrong letter, over super operator C. And it looks like this: 1 to infinity minus I lambda to power n integral from 0 to t C of order n depends on initial time and time s ds. Okay, and this ordering is over all the superoperators C. So what I mean by that, if you take TC and let's say you take some CK, S0, some CL of T0, and if T is greater than S, this time ordering resolves into CL T0, C S0, K. All right, so the ordering treats all the C Ks on equal footing. So in other words, this thing here, we can write it as a series. So this is like, so this is series that goes from n from 0 to, let me check my indices. You know what? Not enough room. I need more room to write it down. ECI sum CNS0 ds. It's in other words, sum over n from 0 to infinity minus I lambda. No, not. I'm sorry. I'm just sloppy today. 0 t dsn. So time ordered integration, and the things that we integrate are actually all the whole series at the same time. Okay. K C K S N 0 CK1 to infinity minus I lambda K C K S1 0. Okay. So this is what I mean by this time ordering. It's coarse-grained enough. It's graining C's. And C, this super operator C, those will be supercumulants. Supercumulant. All right. So this is a definition. It might be incorrect and it might be nonsensical. So the only way to find out is to check, right? And the method is the same as with cumulants. You expand left-hand side and right-hand side, collect the terms of the same order in lambdas, and just compare them. And if everything is fine, you will be able to progressively go order by order and solve the equations and find what C's are. And and surprise, surprise, because we are dealing with exponents here, I think at least this is the explanation. Everything is fine. Okay, you can actually solve it. This is supercumulants are well defined for this implicit definition. And to show it, we can do some calculations. Okay, to get a couple of them. So again, for simplicity, because they will get real complicated real fast. So we will assume that the process is Gaussian, still assuming process is Gaussian. and zero average. Okay, so that we don't have like whole zoo of terms. So if we assume that f is g and g average is zero, then okay, so let's so the procedure is simple. Expand this in series, expand this in series, and compare. So let's take left-hand side. So we get lambda to zero term would be just identity. Lambda 1 term would be integral g average as vs ds, right? Because it's this exponent, right? So it's that would be the first term. Second term would be plus minus I lambda squared, right? And time ordering for V, ts2, ds1, s1, gs2, gs1 average, vs2, vs1, and the higher order terms. We won't go, I don't want to go beyond that on live. Okay, it's just, and this again, bullet is identity, right? I mean, the lone bullet, free bullet is just identity in super operator speak. Okay, so right-hand side. Lambda zero. So remember, it's a, sorry, is it too far? It's an exponent of whole series, right? So there are all the series has all the orders of lambda, which is then compounded with the fact that it's an argument of exponent. So it's like, if you recall what we did with cumulants, it was like the stuffs got mixed really fast, and but still under control. So zero order is bullet because the series starts from first order. Okay. The first order is very simple. It's just one first order supercumulant. So minus r lambda to power 1, 0 t cumulant of first order S0 ds. Mm-hmm.
That answer. No, the integral is 2. Then the integral after
2. Yes. Thank you. Keep me in check here. I'm really sloppy today. Yeah. Of course. Time order. Yes. And this so second order. So things proportional to lambda square. Actually, even minus lambda square. We'll have two contributions because you take two contributions. I don't know how to say it. It's 0t ds2 s2 ds1. You will get second order. No, sorry. I'm sorry. I'm extremely sloppy today. SC2 S0 ds. Okay, this is the easy part, but there is another term lurking. It will be time ordered because we are ordering over all C's. ds1, C1, S2 0, CS1 0 of order 1, and higher orders. Sorry about that. That was really like, again, sloppy of me. Right? You can imagine what's going on here, right? Because you take like the first non-trivial order of exponent will drop down the whole series. And in this series, you have a lambda square term, which is C2, right? But also like the second order from the expansion of exponent, we have two series times series. And both those series you find the first order terms, then combine into second order. This is where this one came from. Because everything is ordered, time ordered, you have time ordering here as well. All right. And now you can you can easily check. Okay, so C1 as 0 is G as average VS, okay, which is 0 because we assume that the average is 0, right? That was our assumption. That's good. If C1 is 0, then those guys will disappear, right? So the second order is easy to find that C2 has 0 equals integral to S average S 1 VS VS1 DS1, which comes from here, right? If those guys weren't 0, they would come in and combine with the average here to form a second cumulant, essentially. So because average is 0, this is you can actually safely write here a second cumulant. Okay. You can check that third one would be 0 as well. Okay. And the fourth one, I don't want to write it down. Okay. This one is it's scary. Although I can show you I can show you how it looks like. This is how it looks like. There are two lines. Okay. This one line, oh, it's not so bad, but there's a second line. So the thing that happens here, you get like a commutator, so for V's, okay? You get, for Gaussian, so at max you will get second cumulants here, but the V's start to really, entangle with each other. You get some commutators. This you can also write as some combination of commutators if you want, but there are things that are getting crazy here. And you can imagine that go up the ladder and the things just blow up, and if process is not Gaussian, it's even more terrifying. Okay. So I won't write it down here, in other words. But it can be written. The point is that it can be written, can be found, even for non-Gaussian processes, even with non-zero average. And as a matter of fact, I think I have for you an assignment. Oh, later. There's assignment to check it out for yourself. But whatever the case, this is a good definition. Okay, supercumulants, like standard cumulants, are well-defined objects. Okay, we can work with that. And as a matter of fact, we will use it now to actually deal with computability problems of stochastic maps. Okay, because we just showed. What is it? Okay. So we just showed that stochastic map in all its glory can be written as time ordering over supercumulants of the supercumulant series here. Zero T, supercumulant, and TS, okay? And because this time ordering treats all supercumulants on equal footing, well, we can just apply disentanglement theorem. Remember the one from way back where the interaction picture and stuff like that. So we can like split this series into two pieces and like pull out one of the pieces outside. The piece that has finite number of terms specifically. So we can like, oh, we're using my cursor here, so small. So we can like, C looks like E, I'm sorry for that. The calligraphic font for C is difficult to write down. So let's split it. N goes from 1 to some N0, all right? Minus lambda, 0T, and S0 ds, plus the rest. So let's say this is K goes from N0 plus 1 to infinity. This one is in infinite. K lambda T CK S0 ds. All right, and now let's do disentanglement. Let's pull out this part. So we are pulling out this from N to N0. So now there is a finite number of supercumulants, which in principle can be actually calculated. And you can obtain a finite form superoperator. And let's call this bad boy UN. Okay. And we have the rest, which, if you remember, if you are pulling out, doing disentanglement, then you are switching into interaction picture in the what's left. So we have to have a new symbol for interaction picture here. So let me just use tilde here. K goes from N0 plus 1 to infinity minus I lambda K C tilde K S0 ds. And tilde, what this means, C tilde S K 0 is U and the thing that we disentangled from 0 to T, from T to 0, sorry, C K as, oh no, S, time point is S, from 0 to S. Okay, so this is tilde. This is a we're just doing disentanglement theorem. And you know, this all will make sense for us if you know, if the thing that's left here is kind of small, so maybe it could be neglected. We are building here a perturbation theory essentially. So let's just let's write it down as a. So let's take this exponent and expand it into series, right? To show that the corrections in explicit terms. So we would have here T0 n, so our approximation. How do you want to write it? Plus I lambda n 0 plus 1, 0 T U TS N average C N0 plus 1 S0 U N. Why am I so stupid? This should be N0. I'm so sorry. Oh, I'm so sloppy today. It's supposed to denote the order at which we cut. I'm so sorry about that. 0, and you have higher order terms. And the idea is that the idea is to construct an approximation, right? So we have a full super-cumulant series. You want to cut it on some finite term to get this U and 0 guy. And this is probably work well if the remainder is small in some sense. So our approximation will in our approximation we obtain this U bar and 0, okay? And this is a formula for the first order correction if you need it. If you want to check if this is how big error is, this is the formula you would use to obtain this next and next corrections. And now, yes.
A little bit up. There following starting 15 and then there is the 12. Is this starting from one equation or is this another thing?
Yes, this is one equation. This is what we did here is we applied this entanglement theorem. Okay. If you need to refresh your memory, you have to, lecture 2 perhaps. Remember, so you have exponent of sum of operators, right?
Right. Yes.
And you when you pull out, then you get the time ordered.
Yes.
So this is what happens. Because you get this interaction picture of what's left. So this is a recipe, right? And now, important thing, because this is a finite form, in principle at least, finite form superoperator, this guy here is computable. See, this is time ordered combination of C's. So this thing automatically, by construction, it satisfies dynamical equation. So in other words, I lost my cursor, here it is. dt u n, whatever n is, wherever you want, you make the cut. This will give you sum over, I don't know, k from 1 to n minus I lambda k c k t0. So this is a finite number of terms here. U and t0 with initial condition 0, 0, and is just identity. As a time ordered exponent, where you order over the whole, this coarse grain ordering, this is by definition, by construction, it satisfies dynamical equation, so it can be integrated numerically, or maybe even if you are real good, maybe even analytically. And on top of that, equivalently, it also satisfies the composition rule automatically, because if time ordered exponents that satisfy dynamical equations, it's the same as saying that there is a composition rule. So you also have this, so Ts S0, and although you have to you have to compose the same same UN. If you want to mix different orders, that won't work because those would be completely different super operators. And T0 and what is, if you want to say what is this TS actually? So when it starts from S, not from 0. Well, there is an answer to this as well. Okay, from 1 to n minus I, and it's of course again very intuitive. Okay, I used up S Q0 du. Although notice, due to composition rule, this is how I mean, if you combine all this stuff, the formula for U that starts from S to goes to T is, the limits translate into limits of this integration. However, notice that this supercumulant still start at 0. Okay, the first initial condition is still encoded in the supercumulants. Okay, all right. This is an important thing. The origin matters here. Okay, where you got your approximation, that you got it from here, it matters. It matters that it started from 0. Okay, just a thing to remember. But all this makes UNs computable, of course. If you have equation, you can integrate it. Therefore, it's computable. And so this kind of solves the problem of stochastic maps. This is the recipe. Okay, this is how you handle this with this invention, this method of supercumulants. You also have a recipe for calculating corrections if you need them. If you want to check, for example, if your approximations are good, or maybe you want to, get more precise results or whatever else. It's all calculable, computable stuff. Because to calculate the correction, you need the supercumulant, which you can obtain, but you also need to, propagate it with UNs. So to calculate correction, you also have to first integrate your UN. That's from technical stuff. If you will be forced to do it, then this is how you have to do it. But it's all, again, doable, computable, finite number of time and steps required to complete this. So this is the solution to our problem of computability, which is kind of neat. And to finish this part off, I want you to indulge myself again a little bit, because I want to make it a 5 minutes of appreciation of this method of specialized time orderings. Okay, because this is like, oh, notational. This is just a notational convention. Okay, what's a big deal? But check out the following inscription. So one of the forms for stochastic map was this. Here, right? So this is the original stochastic map. So time ordered X, ordering over V's, average, and you can absorb average into cumulant average with time ordering also V, right? So let's assume F is G and 0 average, and write it down. So on one hand we have So we have this inscription, E minus lambda square 0t ds2 0 s2 ds1. We have second cumulant ps2 ps1. But now I can, I can write it as E minus lambda square integral ds2 c2 s2 0. Because this, I recognize in this the formula for the second cumulant, supercumulant, right? This is just the same formula. So let me write it like that. Okay, that's okay, that's okay. On the other hand, so that would be, so this is u t0, okay? On the other hand, we have our approximation. If we set to 2, second order, that would be t ordered over c e minus lambda square 0t ds2 c2 s2 0, right? It's like the same exponent here, both time ordered by the difference, but there's a huge difference what kind of time ordering is here, right? So of course, this thing minus lambda square 0t c2s 0 ds, it's not the same as t c e minus lambda square 0t c s0. Yeah, they are not the same. In fact, this guy is a second order approximation of this guy, right? They are not the same. And the difference is in this time ordering, specialized time ordering. And now imagine for a moment if we didn't have this invention, if we just have t. Nothing would make sense here, right? And imagine now trying to construct all this supercumulant method without having this this method of time ordering, specialized time ordering, okay? It would be complete nonsense. But there is a paper where people try to do that actually, and it's very weird. So this time ordering, it's like kind of in-house invention, although you can find places in literature where people also use this, but you can also find many famous papers where people don't use this convention, just have t, and that there are very famous papers by very famous and brilliant people who, based on this inadequacy in their notation, wrote whole papers about some perturbation theories that are just wrong because they were incapable of doing this kind of distinction. Okay, whole papers, whole generations of physicists cited them and used them, and they are just wrong. Okay, so 5 minutes of appreciation for specialized time ordering. Okay, take care about being specialized in this sense. This is very funny, but it's cute. It's very cute. So this is, if anything, if you were to learn one thing from this whole course and forget everything else, remember this. Okay, remember this time ordering stuff. Okay, the rest you can just throw into the bin. Just remember this. And that would be that. Okay, that was indulgence for me. Thank you for allowing for that. And the final section, and actually the end of the second part, will be section 3, and we actually will we will end before we'll have some extra time. Sample average. Yeah. Here we go. We have time. No problem. All right. Sample average. Okay, so the super-cumulant method, cumulant, super-cumulant, all that stuff was right. So we tried to figure out how to deal with the average, right? Because a new complication in stochastic maps is this extra averaging over stochastic process. But there is so I was talking about okay, so you have average, you integrate with probability distribution, but from theory of probability, we know that this is the same as doing the arithmetic average over samples. You can like imagine that if you get samples from your probability distribution, and then just substitute them and sum up the results, right? Divide by the number of samples. So that's what I mean by sample average. In other words, to be a little bit more precise, so our stochastic map, which is on the one hand, time ordered V, lambda T, F, S, V, S, ds. So it's average. Average means integral probability distribution. But according to the, how probabilities work, this you can, it's the same as taking limit sum j goes from 1 to infinity tv minus I. I'm so sloppy today. Just kick me in the ass. Right. You integrate over trajectories. Lambda 0t fj as ds. And well, divide everything over n. Where and maybe ensemble. Ensemble of sample trajectories. So we have a set of trajectories. J goes from 1 to, I don't know, infinity, right? So if you can like get your samples, draw them from your distribution, you can calculate your average not by integrating with distribution, but just substituting samples and just adding up what I wrote here, okay, right? And this, of course, strictly speaking, to get the equality, you have to go with infinite number of samples. But you can do some approximations where you just cut it on. Don't go to infinity. Just cut it on some probably quite large number of samples. And let's write it like this, fj. Okay. So this is what I call the sample average approximation to stochastic map. So it's from computational point of view, it's kind of, if you have access to large enough ensemble of samples, so something like this, with large enough number of trajectories, the problem of computing U bar is reduced to problem of computing large number of unitary maps that have a substituted trajectory. Sorry, that have substituted trajectories, right, from your ensemble of samples, and then adding up, dividing by the number. So since unitary maps are, let's say, trivial to compute, this makes it laborsome but trivial to calculate the sample average. So why bother with this super-cumulant expansion in the first place, if this is how you can do it? Well, where do you get your samples? This is the problem, right? How do you get your samples? Sometimes, for example, if your process F is a Markovian process, well, then you can try to numerically generate your samples. And for Markovian processes, this is like a convergent procedure, right? You can actually do this. If you did one of the assignments, you even have a code in your back pocket that generates trajectories for you. So this is kind of easy. But Markovian processes are fairly rare. If they are not Markovian, then there is no like universal method that works every time. There are sometimes you can do stuff, but in general, it's just hard to get this ensemble of samples. It's just difficult. Although if numerical methods don't work, are unfeasible for some reasons, there is also another scenario, because you see, in certain physical systems where the stochastic map description is actually warranted, for some systems, there's actually possibility to directly measure those trajectories. This is not always the case. The system has to satisfy certain conditions, but sometimes it's actually possible to just, load your ensemble with directly measured samples, and then store them on your hard drive, and then just use them to calculate the sample average of your simulation or something like that. Okay, sometimes it's possible. We will talk about this scenario at the very last chapter of this whole story, but sometimes it's possible, although in general, you cannot count on that. Therefore, if you have access to samples, go for it. It's much easier it's much easier to get a approximation that's fairly accurate. Okay, it's much easier to calculate this, but always remember that most likely you will have to go for some super-cumulant expansion in the end anyway. For that, you don't need samples because the averages are built in already. And yeah, that's it, guys. That's it. That's all. So let me just assignments. Talk about some assignments. So one assignment was I believe 23, to check out the this formula, to verify, to look at it. Don't look too closely. Don't look into Abyss, because Abyss can look back. Next one, it's also for inspection. 24 is to actually find the fourth super-cumulant. I just flashed it to you at some point. Yeah, I just showed it here, right? So actually to get there, so to get to fourth, you have to go through first, second, and third, right? But the trick is, don't assume that process is Gaussian. Although assume that average is zero. If you don't assume average is zero, it's even more terrible. So again, I don't expect you to just to do the calculation step by step, but check out the solution to see what you are missing. Final assignment, which I like you to, so this is kind of maybe a bigger project to maybe do it, take your time doing this. But consider the stochastic Hamiltonian like this, okay? And compute the stochastic map generated by this Hamiltonian using the sample average, so one method, so this one, okay? And the second order super-cumulant expansion, so super-cumulant approximation when you cut on the second order. So essentially, it's essentially this, okay? For f equal to random telegraph noise, which you have samples for, you know how to generate them, and you can calculate the moments and all the other things. In addition, now do the same for a process that's combination of independent random telegraph noises, and take enough components to make it close to being Gaussian, and then do sample average versus second order super-cumulant expansion, and experiment with various settings of the parameters, because as you imagine, second order approximation won't always be the best approximation. If your parameters don't line up, cutting the super-cumulant series on the second order might be just, error might be big because the higher order super-cumulants are just more important. However, as the coupling becomes weaker and some other parameters become smaller or stuff like that, the higher order supercumulants become less important and the second order becomes more accurate. The sample average is kind of immune to all those considerations because it's the closest thing you get to like exact calculation, provided you can generate trajectories. So, do some investigations. I would expect you can take your time with this. Make it a project for a couple of weeks, maybe. Okay, just play with this for your own benefit, right? This won't be wasted effort, believe me. Okay, this stuff will be useful. Again, in solution, you have a if you are lost, check it out to see the instructions how to proceed. But I think it will be satisfying to get a real code, and plot some plots and see how it all behaves. So with that, I think we can finish for this week. Next week we go to open systems, real open systems. Okay, finally, at the end, we get to open systems.